So next up, I'd like to introduce our second speaker, Dr. Oakes, on developing fiber microsystems for a variety of applications. And today she's going to share with us a parametric study of functional fiber integration into woven textile.
You're on real quick.
We can just hear you, Lauren.
Is that better?
A little bit. If you could come closer to your mic, or
Is that a little bit better?
I think we can hear you now. Yeah, that's
okay.
Great.
Sounds good. Thank you for the introduction, Meg. Appreciate it. Looking forward to sharing our work with you guys today. As Meg mentioned, I'm with MIT Lincoln Laboratory, a technical staff member there. And so before kind of jumping into the meat of the talk, I'll just quick give an introduction of Lincoln Laboratory and how we became to kind of be involved in e-textiles. So for those of you who are unfamiliar, Lincoln Laboratory is a federally funded research and development center located in Lexington, Massachusetts. We do work on a variety of projects with campus, but we are a separate facility located just outside the city. Our mission is to develop technology in support of national security. So the lab has a wide range of mission areas spanning air traffic control, communication systems, cybersecurity, to name a few. Our work with e-textiles and our team is really located in the advanced technology mission area. And while our team is part of Lincoln Laboratory, we do work closely with AFOA, the Advanced Functional Fabrics of America Institute. I know some of you are probably very familiar with AFOA, but for those of you who are not, it's a Manufacturing USA institute focused on transforming traditional fibers and textiles into highly sophisticated devices and systems. And along with that, building the ecosystem necessary for advancing textile development.
Excuse me, Lauren,
we'll interrupt you.
But
are you sharing slides right now? Because
I am.
We can't see them. Oh, okay. So we cannot see your slides.
What are you guys looking at right now?
We're looking at a message that you've started screen sharing, and double click to enter full screen mode, but we're not actually seeing any slides.
Oh, so it's just a black screen at this point?
Yeah, with some text.
Okay. I've had this happen before with Zoom where it's just slow to kind of upload or send the charts. I guess our options are, I can try and stop and reshare and see if that works better. Let's see.
Could you try that first, and then I think we have a backup
okay.
slide deck.
Can you guys see that now?
It's the same message. Chris, do we have a backup?
Yep, I'm grabbing.
Perfect. All right. I will stop the share and let you present, Chris. Sorry about that, everyone.
That's okay. It was interesting to listen. But, yeah, I thought there might be some visuals as well.
Yeah.
Give me just a second. I'm just trying to get over to my screen share now. I have
no problem.
How's that?
We can see your slides.
Right.
All right. So I will kind of skip over this part. If you want to jump maybe to slide 3 or 4, Chris, I can kind of pick up where I left off. As I mentioned, Lincoln Laboratory is an FFRDC, and we work closely with AFOA as well. So AFOA is Advanced Functional Fibers of America. And for those of you who are not familiar, they're Manufacturing USA Institute focused on developing advanced textiles and fabrics. So about 3 years ago is when the Defense Fabric Discovery Center was stood up. And so that is a facility that has been built up in collaboration with AFOA as well as with CCDCSC, located at MIT Lincoln Laboratory. So this is where we got our start really in e-textiles and developing functional fibers and fabrics. This facility is specifically aimed at developing functional fibers and textiles targeting defense applications. And we work closely with AFOA and CCDC on a variety of projects. So if you jump to the next slide, Chris. This is a quick snapshot of our facility. We basically have capability to do end-to-end rapid prototyping of functional fibers and textile systems. So starting at the front end, fiber simulations, looking at how these fibers and fabrics behave mechanically, electronically, thermally. We have the ability to then actually build those fiber and yarn devices, manufacture those, as well as integrate those into textile systems through weaving and knitting. And then finally, that last systems integration piece, really be able to test and evaluate the full textile system there. So I'll just mention again, it is a collaborative facility between Lincoln Laboratory, AFOA, CCDC, as well as the state of Massachusetts. When this was first stood up, the state of Massachusetts definitely we had support from them in terms of building this facility to begin with. So really a range of organizations working together and invested in really developing functional fibers and textiles. So if you go on to the next slide, one of the advanced textile products that we have the capability to create is functional fiber microsystems, is what we like to call it. So if you click ahead, Chris, there's I think it's a build chart here. On the left is a traditional fiber. So this is a traditional filament fiber from a textile, and you can see it's a single material, a single architecture, kind of a cylindrical shape all along its full length. And with that comes a single functionality. At the DFDC, we have the capability to build what we like to call functional fiber microsystems, which basically integrate multiple materials in a more complex architecture, all within that same form factor. So the picture here, you'll see we have metal conductors and semiconducting rings surrounding a hollow core, and all that within a polymer cladding. So this is similar to the image on the left. We're on the same order of hundreds of microns in diameter and the same kind of kilometer length scale, only now a specific fiber is able to sense incident light on its surface and also direction of that incident light. So basically, with the same size, diameter, and length scale, our functional fiber microsystem has the same size as a traditional fiber, but with that additional functionality. So in the next slide, the way that we make these is through a process called preform to fiber drawing. This borrows heavily from the telecom industry and how they make optical fibers. And the idea is basically that we start with what we like to call a preform, which is essentially all of the components, materials, architecture that we intend for the final fiber, but assembled at the macroscopic scale. So this preform then gets heated in a furnace, and as that material starts to heat and flow, we can pull that down into the micro scale. So that's the image in the center here. What's unique about this process is that all of the architecture that's introduced at that macroscopic level, that gets preserved in the final form of the fiber. So it really is an elegant way to kind of transition down into micron scale, micron length scales. And this is a conservation of volume process. So as your height and width shrink down, that length extends. And so with a single preform, we're able to get kilometers of length of fiber. On the right-hand side are just a couple examples of the types of functionality that we're interested in incorporating. This is by no means an exhaustive list, but it does kind of touch on some areas of interest for us. So light emission and detection are useful for optical communication, also other types of optical sensing, such as heart rate or SpO2. We're interested in a wide range of sensing modalities, so temperature sensing is in there as well. And then finally, those last two examples really kind of target being able to control the appearance of your fiber or your fabric. And so color change is one kind of application there. So at the end of the day, what we basically have is a filament fiber with this additional functionality. That can be used independently by itself if the application calls for it, but another thing we can do is then integrate that into a textile system. So next slide. Here you'll see several examples of our functional fiber microsystems being integrated into textile products. So this work here was done by AFOA along with their member companies. And they really have some kind of impressive demonstrations here integrating functional fibers into a wide range of textile products. So kind of ropes and yarns as these one-dimensional textiles, but also wovens, knits, composites as well. So now that we have this really elegant demonstration that this integration is possible, and integration at the kind of manufacturing level where they're using industrial scale looms, knitting machines and whatnot. The next step is to characterize the textile's performance, not only looking at kind of the durability and reliability of the electronic device, but also what we want to understand is how the incorporation of these devices impact the base textile's intrinsic performance properties. the goal is to add electronic functionality, but not at the cost of altering the hand or the feel of the textile itself. And you'll see as we go along here that that's really the goal of kind of what this study is targeting. So next slide. Now that I've kind of introduced the technology capability that we're focused on, I'll describe a little more about the parametric study, its scope and methodology. I will mention that this is still a work in progress. So, even up to this week, we're still kind of acquiring the bulk of our data. But I think sharing with you guys today the setup for the study and our intentions with it will still be meaningful to share more broadly. So with that, we can go to the next slide, Chris. And we'll start by thinking about what defines the performance of a textile or fabric. So much of a textile's behavior is really due to its constituent components and how those pieces are put together. So the material of the yarn, the weight of the yarn, that weave structure, all those design choices impact the final textile's performance properties. So while there's a long list of individual properties that can define a yarn, and in here we just name a few, what we can then do is distill those down to a few key performance parameters that really describe the yarn's behavior and subsequently the fabric's behavior as well. So in the middle column is listed the parameters that we've chosen to explore and really focus on with this study, with a keen interest in the mechanical behavior and the hand of the fabric. The flexibility of the fabric is one thing that really makes an e-textile unique compared to rigid electronics. And so we're really focused on trying to be able to preserve that quality as much as possible as we start to introduce these additional functionalities. So an example of how those yarn properties really can be combined to produce values for our identified key parameters. We can look at the analytical expression for yarn bending stiffness on the right. So this expression incorporates both materials properties, such as your elastic modulus, but also structural properties. So the number of filaments, the size of the filament, the twist, which has to do with kind of the geometric orientation of those filaments in relation to each other. All those properties together, describe the stiffness of the yarn, or basically how easy or difficult it is to bend. And you'll start to notice that at this point, we're looking at more complex textile structures. So initially I showed you micrographs of the filament, right? Here we're looking at yarns, and eventually we're gonna start looking at fabrics as well. So with an understanding of the constituent yarn properties and how they contribute to a final fabric's performance, we can start to compare how our functional fibers and more broadly smart yarns, how they compare with traditional textile yarns. So next slide. So here is a snapshot of traditional yarns compared to more broadly smart yarns. I have our functional fiber here, but also we can consider flexible PCB or even a monofilament conductor could all kind of fit into that smart yarn category. And as we look and compare these yarn properties, you'll see that some things are similar, such as the overall yarn diameter. We're about the same order of magnitude, around 1 millimeter or so. But there are also striking differences. So one would be the structure. Traditional yarn generally has a multi-filament structure with each filament, 10 to 50 microns in diameter. Whereas given that now our smart yarns here are monofilaments, they're, are the yarn diameter, so 1 millimeter or so. And then also material differences, right? As we start to incorporate electronic functionality, we need conductors, semiconductor materials as well. And so next slide. As you likely expect, these differences in yarn properties manifest themselves in differences in the yarn performance parameters. So kind of honing in on those key yarn performance parameters that we focused on earlier, yarn packing, bending stiffness, axial stiffness. Most strikingly, we can see that the bending stiffness between a traditional yarn and a smart yarn can be orders of magnitude different, which I think all of us here have at least kind of qualitatively experienced that, right? A traditional yarn and one with electronic functionality, the notion that those have different behavior, that one might be stiffer than the other is not by no means a revolutionary idea. But what we're trying to do with this work is really quantify those differences such that we can better understand and address the requirements a smart yarn needs to meet in order to have a more seamless integration with traditional yarns. Next slide, Chris. So just to illustrate that point a little further, quantifying the performance comparison. Here we can look at a simple case example comparing bending stiffness of a monofilament smart yarn compared to a traditional 260 denier multi-filament. And so on the table or on the graph on the right, basically we have monofilament smart fiber diameter on the x-axis. And on the y-axis, we have the ratio of bending stiffness of the monofilament compared to the traditional yarn. So basically, when that ratio is equal to 1, we have equivalent bending stiffness between a traditional yarn and our monofilament smart fiber. Plotted here to kind of bound the problem, we have a completely copper monofilament plotted in blue and a completely polymer monofilament plotted in red. And so basically using this graph, we can see where those lines kind of cross this equivalent bending stiffness line to tell us what is the size of the monofilament that we need in order to match that bending stiffness. So here we can see that's about 100 microns in diameter. So the next step is to consider, is this 100 micron diameter enough real estate to impart the desired electronic functionality and to address any thermal management considerations as well. But really this is a nice starting point, at least to define the mechanical requirements we need to meet in order to kind of have comparable behavior with our fabric. This is not to say that you can't put a larger, smart fiber into a fabric, but it does indicate that at a larger size, you'll start to affect the bending performance. And we may need to address that discrepancy in yarn bending behavior with fabric level integration strategies. Next slide. So with that, I'll describe kind of the full scope of our parametric study. I hope the previous few charts kind of clearly illustrated what we're trying to address, namely the question of how can the incorporation of functional fibers add electronic capability while still preserving a textile's original performance characteristics. Previous charts focused a comparison on the yarn level, and now we're starting to extend our understanding to the fabric level as well. So here there's some additional parameters we can be manipulated to potentially account for differences at the yarn level, such as the cover factor or how many picks are inserted with your monofilament as opposed to a traditional yarn. To help narrow the focus of a study, we decided to target fabric classes that are most often used by our sponsor. So we targeted 3 fabric weights, light, medium, and heavy, and then used nylon or polyester as our base yarn. We wanted to be able to extend our results to a range of smart fiber architectures so that they're then used specific functional fiber system. We chose to use a nylon monofilament as a surrogate smart fiber in this study. So in parallel with an analytical approach, we're fabricating a wide range of samples, combinations, and subjecting them to a suite of textile testing methods to characterize the fabric performance. Not all the performance parameters of interest can be accurately deduced from analytical expressions. So carrying out this experimental tests are really key for us to get a good understanding of the impact. Samples with and without fiber surrogates have been fabricated so we can compare against a control. And ultimately here the goal is to end up with a starting set of requirements that need to be placed on the fiber in order to maintain the host textile's original performance. So if you go to the next slide. Here's the full scope of the study. We have basically 53 distinct fabric samples that were produced covering 3 fabric weights, 3 finishes, 2 cover factors, and 4 monofilament diameters. So there's a wide parameter space that we're exploring here to really understand the effect of the monofilament. Next slide. And here's just a snapshot of what those actual samples look like. So on the far left is the control of 100 denier polyester. And then just to the right of that, we've inserted 100 micron monofilaments. So the monofilaments are in black and the control yarn is in white. On the far right side is a little series of images from our 1,000 denier polyester samples. So the top is the control, the middle has 100 micron monofilaments, and the bottom has 900 micron monofilaments. You'll notice in the middle, the monofilaments are actually smaller in diameter than the 1,000 denier base yarn. So there's actually 4 picks of the monofilament for every single 1,000 denier yarn there. Next slide. Here is a summary of our testing plan. So as I mentioned, our testing is still currently underway, but we chose to do kind of 4 test methods to characterize all 53 samples in terms of their kind of mechanical performance and their hand, along with 3 additional test methods to kind of targeting depending on the sample's finish and whatnot. We more selectively decided to apply those tests. So again, the output of those tests is going to be these key fabric parameters. They're really targeting mechanical performance, so stiffness, permeability, that kind of thing. And then finally, really linking this back to the fiber requirements. What kind of diameters, material composition, cover factor, what requirements need to be placed on the fiber in order to have that seamless integration. So we can go to the next slide. There we go. Thanks. So here, like I mentioned, we have our fabrication complete and we're having testing underway, but we're currently in the process of testing everything. Here's a couple initial samples that we've been able to kind of play with and look at qualitatively though. So even qualitatively, we begin to see some differences between the samples and can compare with our analytical predictions for how we expect the fabric to behave. The far left is the 1,000 denier control sample. So Chris, if you want to play the video. I hope this works. You can kind of start to see the hand and how that fabric looks and feels as it's manipulated. In the center is the sample with 100 denier, or sorry, 100 micron monofilament. As we play that video, we can see that qualitatively the kind of manipulation and hand of that fabric appears to be similar to the control. And then on the far right, we have the 900 micron monofilament. And this you can see is distinctly different. It's retaining the kind of stiffness of the monofilaments as we move and bend it, and clearly has different behavior than the control sample itself. And so what we've seen in these videos is all consistent with our analytical predictions. So in the table in the lower left, we have the ratio of bending stiffness again. So of the monofilament inserted samples compared to the control. And you can see at that 100 micron level, we're getting close to a value of 1. So similar, what we would expect, kind of consistent with the qualitative observation. And then at the 900 micron insertion, we have a significantly stiffer fabric, also orders of magnitude stiffer in terms of the theoretical prediction there. So this is some initial observations that we've had just looking at their samples qualitatively. If you go to the next slide, Chris. Another observation here is in terms of increased transparency. So if we think again about the 100 micron monofilament insertion, it appeared to have similar bending stiffness, but there does appear to be other types of differences that aren't captured in that stiffness value. And so here, looking at the transparency with this high fill factor, high cover factor of monofilament, we can start to see that the fabric actually has a higher transparency than the control. And this is due to the difference in the yarn structure. So where the traditional yarns filaments have some hairiness and texture to them and can move relative to one another and fill the gaps, between the different picks. The monofilaments are rigid cylinders with smooth sides, and so that kind of leaves some gaps for optically being able to see between those. So again, this is some initial kind of results we've had, but as we await kind of our full testing to be complete, I think the real key to this study is going to get those quantitative values back and really be able to put kind of rigid requirements on our fibers kind of moving forward. So next slide. So with that, I'll just kind of draw some conclusions on where we're at with things. Smart yarns and traditional yarns have distinctly different architectures, leading to differences in their performance parameters. And our parametric study is really intended to quantitatively define those differences in performance and relate it back to the initial properties of the yarns and fabrics, such that we can provide a starting set of requirements for our smart yarn development. These requirements will define what a functional fiber microsystem needs in order to retain the host fabric's kind of intrinsic performance properties. And it will not only guide functional fiber integration, but also future functional fiber development. So as we start to look at new architectures and different types of fibers and materials integration, understanding kind of what mechanical needs we need to meet in order to retain that host fabric's flexibility and performance is really key. Lastly, I just want to mention that, while we're focused on functional fibers, a similar approach can definitely be applied to alternative methods of incorporating electronic functionality. You can go ahead, Chris, that's fine. So quick, just acknowledge all the people that we've worked with on this. Warwick Mills has been a great partner in all the fabric fabrication. They're located in Ipswich, Massachusetts. CCDC and Gaston were our partners with all the textile testing, and then AFOA has been working with us throughout the whole process. So with that, thank you. I'm looking forward to questions during the Q&A.
Thanks, that was really interesting. Some really cool work going on there.